Okay, picking up a little bit before where we left off last time, we learned about Lewis structures and resonance structures. And then we went into an extra level of detail because sometimes we'll have situations like where we're putting together a Lewis structure and we think, well, why wouldn't it be B instead of C or one of the other resonance structures of C? And that's where formal charges come into play. So formal charges are made up imaginary charges that we use to keep track of how many electrons each of our atoms has. So our sulfur, our nitrogen, our carbon in the previous example. It's fake, it's made up, it's not real. And we also ignore electronegativity. So we're assuming that we've got pure covalent bonds, nice and equal sharing of our electrons. It's the difference between the number of valence electrons that that atom has just by itself, so based on where it is on the periodic table, what column it's in, and the number of electrons that it's touching or that it owns in the Lewis structure. So that's going to be all of its lone pairs plus all of its half of its shared electrons. So in a bond, it's going to take 1. In a double bond, it'll get 2. In a triple bond, it gets 3. So it's going to take half of those electrons. And for our formal charges, the sum of all of the formal charges in a neutral molecule has to be 0. If it's in an ion, then it has to be the charge of the ion. So it'll always add up to whatever the charge of that compound is. And we're trying to minimize our formal charges. We want small formal charges. Small formal charges means that our atoms are closer to the state that they would like to be in. Ideally, we have a formal charge of 0 for all or most of our atoms. If we can't avoid a formal charge, then we want to put negative formal charges on our most electronegative atom. That's the only time that electronegativity will come into play. And I gave this example of if we have got carbon and oxygen and they're next to each other somehow, and we've got options to have carbon with a -1 or a +1 and oxygen with a +1 or a -1, it would be better if the oxygen has the -1 since oxygen is more electronegative. Where do we find our most electronegative elements? What's our most electronegative element? Anyone remember? Fluorine. Fluorine is our most electronegative element. It's got a value of 4-ish. Yeah, 4. Just remember that it's 4. Fluorine's 4. Our noble gases don't have electronegativity values because they just don't like bonding. And the things that are closer to fluorine are going to have higher electronegativity values. So that would be a way, if you don't have your yellow sheet or another electronegativity inclusive table with you, upper right corner, things that are closer to fluorine are going to have higher electronegativity values. So that's how you could figure out which one should have the negative charge. Okay, let's use some formal charges to determine the best skeletal structure for HCN. We've got options of HCN. I'm just going to skip to the good part. That should be a correct Lewis structure. Or we've got HNC. So we want to calculate the formal charges for each of these atoms. So taking a look, hydrogen is coming in with 1 valence electron because it only has 1 electron. If we cut the bond in half, hydrogen has 1 valence electron. It's got 1 electron on it, so its formal charge is 1 minus the number of electrons that are on it, which is 0, plus 1/2 of the electrons that's in its bonds. And this whole bit here the 0 plus 1/2, 2, that's just from our formula, in case you want to use the formula. Or you can just look at it's taking half of the bond, it's taking 1 electron, and so it's got a formal charge of 0, which is great, that's what we want. If we look at carbon, it has 4 electrons on it, or that it owns. And it normally would have 4 valence electrons, because carbon is in group 14 or 4a. So our formal charge for carbon, 4 minus, it doesn't have any electrons just on it, and it's got 8 electrons in bonds, so it's going to take half of that. That's the 4 that we came up with. So it'll also have a formal charge of 0. And then last but not least, we've got our nitrogen, and we'll do this one in purple. So if we count just the tips of the bonds, that's 3, plus the 2 lone pairs, so that would be 5 that it has. And nitrogen normally has 5. It's got 5 valence electrons typically. It's got 2 from the lone pairs, and then 1/2 of the 6 in the bonds. So it would also have a formal charge of 0. So formal charges of 0 all around, we love to see it. I don't think we're going to be able to beat that, but let's go ahead and do the count for the other one as well. Do we have questions about getting those formal charges? I'm trying to show you both ways. If that's confusing, I can just show you one way. We can just do the formula way. I like the non-formula way, personally. Okay, let's do the other one. So for hydrogen, hydrogen's in the same situation, right? It's just got the 1 bond. It's going to take half of that bond. So 1 minus 1, 1's the number that it normally has, 1 is the number that it has in this particular structure, and so it has a formal charge of 0. It's right on track. It doesn't have extra or too few. And then we would look at nitrogen next, and we'll do nitrogen in purple again. Nitrogen likes to have 5, and it's got 1, 2, 3, 4, because it's taking half of each of those bonds. So it's going to have a +1 formal charge. Wants to have 5, it only has 4, which is 1 fewer than it wants, so it's a +1. Has less electrons than it wants. Electrons are negatively charged, less electrons, less negative, means positive, double negative. Always fun dealing with electrons because of those double negatives. Okay, and then for carbon, carbon, as we discussed earlier, wants to have 4. It's got 1, 2, 3 from the ends of those triple bonds, the triple bond. And it's got the lone pair as well, so that's 5. So our carbon is going to have a -1 for its formal charge. And we can see that we've got the -1, the +1, those will cancel each other out. So overall, this HNC is still going to be neutral. So we haven't broken any formal charges rules. If we had to choose between the one on the left, the one on the right, we've got formal charges of 0 on the left. That is going to be better than the structure here on the right. Questions about that? Yes?
Does the molecular formula usually try to be as close to the most structure as possible?
Are you asking if the HCN tells us what order to put it in?
Yeah.
Not necessarily. There's like a rule for the order of what you're supposed to put in what order. So it's just following the order.
Oh, and it doesn't depend on the stop structure. That's
It doesn't depend on the structure, no. I don't actually know what the order is supposed to be. like 100%. It's just kind of like most people, I think, just feel it out. Like you look at enough chemical structures and you're like, oh, this is just kind of like the order that we write it in. It's sort of like there's some phrases in English where it's like it goes one way or the other. Like you wouldn't say a jelly and peanut butter sandwich.
Yeah.
It feels weird. Peanut butter and jelly sandwich feels right.
Yeah.
It's the same sort of thing, but chemical formulas. Or if you're interested in learning the rules, I'm sure that it's out there somewhere. I don't think I have it in my slides though. Okay. I'm going to give you some time to practice with formal charges. So assign formal charges to each atom in these three resonance forms of N2O, where one of the ends is central. Which resonance structure is likely to contribute most to the correct structure of N2O? So figure out which one has the smallest formal charges. And that's the one that's probably going to dominate. All right, our formal charges. For all of these, we're going to have non-zero formal charges on at least one of the atoms. So we have to pick the best one. Let's find out what those formal charges are. For A, if we're looking at this nitrogen on the left, nitrogen normally wants to have 5. It has 5 valence electrons. Oxygen, just so we have it out of the way for later, wants to have 6 valence electrons, just based on what column they're in. In structure A, our nitrogen here on the left has 4 that are localized. So it's got 4 that are on it. It owns those 100%. Those are only for this left nitrogen. And then it gets half of this double bond. So it also gets these 2 if we cut the bond in half. And so it's got 6. So 5 minus 6, it's going to have a -1 formal charge. For our nitrogen in the middle, it also gets half of each of these bonds. And so that's going to be 5 minus 4, got my order wrong. It wants to have 5, it only has 4, and so it's going to be +1. It would like to have one more electron to be truly happy. And then on the right, we've got our oxygen. Our oxygen wants to have 6 electrons on it. It's got 4 that are lone pairs, and then it also gets these 2 from the double bond. And so oxygen has 6 minus 6, which is 0. So oxygen's perfectly happy here, and our nitrogens are both a little upset. Questions about coming up with those formal charges? Okay, and then for structure B, our nitrogen on the left is going to have a 0 for its formal charges. It's got 2 that are on it, and then it's got 3 from this triple bond, so that's 5. It wants to have 5. It's right on target. Our nitrogen in the middle wants to have 5. It only has 1, 2, 3, 4 from the 4 bonds that it's participating in. So it's going to have a +1 for its formal charge. And then our oxygen wants to have 6, and it has 6 from lone pairs, and then 1 more from that bond, making it a total of 7. So it's got a -1 for its formal charge. And then on C, we've got nitrogen here on the left. Nitrogen wants to have 5, and it has 6 just from lone pairs, and then 1 more from the single bond. So 5 minus 7, it's got a -2 formal charge. Our nitrogen in the middle has 4 electrons on it. 5 minus 4, that's going to give it a +1 formal charge. And that should go down there. And our oxygen on the right wants to have 6, and it has 3 from the triple bond and 2 from the lone pair that's on it. So it's also going to have a +1 formal charge. We can sort of double check our work quickly by just making sure that all of our charges add up. For A, we've got -1 +1. For B, we've got -1 +1. For C, we've got -2 and 2 +1s. So they all cancel out to neutral, which is how they should work. Which one of these can we throw out right away? A, B, or C? C. Why can we throw C out? Somebody else give me an answer. What kind of numbers do we want for our formal charges? Big numbers or small numbers? Small numbers. And C has formal charges for all of them that are not 0, right? A and B, we've got 0 on at least one of the atoms, and then we've got +1, -1 on the other 2. For C, we've got -2, that's a bigger number, and we've got 2 +1s, there's no zeros. So we can toss C out right away because it's got the most numbers that are not 0, and it's got the biggest numbers that are not 0 as well. So we can toss C out right away, and then we have to choose between A and B. How do we choose between A and B? What's different about them? Well, for A, we've got a nitrogen in the middle that's got a +1. Our nitrogen on the left has the -1. In B, nitrogen in the middle has the +1, and the oxygen on the right has the -1. So what we're choosing between, in A, nitrogen has the -1. In B, oxygen has the -1. There's a rule that we have for assigning negative formal charges. Does anyone remember? Yeah, when we have the option of giving it to multiple, when we've got multiple places we can put that negative charge, we want to put it on the thing that has the higher electronegativity value. Oxygen has the higher electronegativity value. And so B is going to be our most stable resonance structure because it's got the lowest formal charges. You basically just throw C out. And it's got better formal charges than A. Since nitrogen, having a -1, nitrogen's a lower electronegativity value than oxygen. The higher electronegativity value basically just means it's more willing to accept extra electrons, in this case at least. So our oxygen is more okay with having a -1 charge, formal charge on it. So it's got the higher electronegativity on oxygen versus nitrogen. It's like a 3.5 versus a 3. Closer to fluorine than nitrogen. Questions? Yeah.
What's the line device for remembering this thing again? Is it Fonkle brick ship?
Fonkle brick ship, yeah. FONCLBRICSHP. Fonkle brick ship. Or if you just have your yellow sheet, then that'll also have electronegativity values on it. Okay, we want to draw the Lewis structure, including resonance structures for diazomethane, CH2N2. For each resonance structure, we want to assign formal charges to all atoms that have formal charge. Fun. So to start out drawing a Lewis structure, we need to lay everything out. We need our skeletal structure. We're told that carbon is central, so we're just going to plop everything onto carbon. All right. So we can put everything onto carbon. And then connect it all with bonds. However, this isn't the only possible configuration. It's also possible that we have the nitrogens bonded to each other. Nitrogen can bond more than once. The reason that we're putting the hydrogens on carbon is because it said that carbon was the central atom. And I don't know that we're really going to get much in terms of resonance structures if we draw it like we drew it here on the left. But Lewis structures would tell us formal charges would help us get to the correct Lewis structure. So you would have to draw out both configurations, figure out which one has better formal charges, and then go about going through resonance structures. Okay, so let's do a valence electron count real quick. We've got hydrogen, 2 of them. They each supply 1 valence electron. We've got a carbon. That's going to give us 4 valence electrons. We've got nitrogen, 2 of them with 5 electrons each. So that's going to give us a total of 16 valence electrons to place. And we already used up half of them just getting everything connected. So that means that we are going to need to plop in 8 more electrons. And it's actually simpler than I said. We can actually rule out the structure on the left just after placing our remaining valence electrons. So if we look at our hydrogens each have 1 bond. Hydrogen only takes 1 bond. It never takes more, at least in this class. And so our hydrogens are happy. We do not need to give them any more electrons. They've got their full duet. Carbon in the middle has 4 bonds with 2 electrons each, so it's got 8. So hydrogen's happy, carbon's happy. That's going to be the same for the hydrogens over on our other option for our structure. So carbon's happy. That means we can add the rest of our electrons to our nitrogens. So 4 electrons to each nitrogen. There's 2 of them. So no electrons left. And for this one over here on the right, we would still need to add in those 4 electrons. I like to start working from the outside in, so let's do it that way. We do not have full and complete octets yet on either of these. If we look at our structure on the left, our nitrogens only have 6 valence electrons for their octet count. Our nitrogens each have 4 in terms of lone pairs, plus 2 more from the bond. How can we get our nitrogens to have more electrons? We can't. If we were to try to increase the number of electrons that our nitrogens have, we would have to share between the nitrogens, but triangles explode, so we can't do that. So that is not a good Lewis structure. We cannot come up with satisfactory octets. Carbon cannot have an expanded octet because it's too small. It doesn't have access to the 3d orbitals, those extra pockets to put electrons in. So that's out of the picture. And that's how we know that it's going to be some variation of the structure on the right. Fun stuff. All right, now that we've ruled that out, we have the true Lewis structure, but we don't have our octets yet. If we look at our terminal nitrogen, 2, 4, 6, 8 valence electrons, this nitrogen is happy. The nitrogen in the middle has 2, 4, 6 it is not happy. Our carbon also has 6, it's also not happy. So we need to get more electrons in the hands of our carbon. We can do that by moving this lone pair in. And now carbon's happy, it's got its 4 bonds for 8 electrons. The nitrogen in the middle is still not happy with an octet though. And so that's when our terminal nitrogen is going to come in and save the day. So we should arrive at something that looks like this. Because of these double bonds, we've got some options for resonance structures. We've got at least one option for resonance structures. So duplicating that, a resonance structure that we can come up with, we can plop one of these lone pairs into the bond, and then plop some of these electrons from the left double bond to go ahead and hang out on the carbon only. Can anyone think of any other resonance structures? I'm not coming up with any either. So it looks like we've got 2 resonance structures, and hopefully I'm correct about that, it's just 2. So we'll draw our arrows, our double-headed arrow between the 2, and then let's take a peek at our formal charges. Our hydrogens are not going to have a positive or negative formal charge. They'll be at 0 because they've got 1 bond. Hydrogen, basically always happy, very easy to please. Love that for hydrogen. For our carbon and our nitrogens, we do have to do a formal charge assessment. So let's look at the right one first. So our carbon here has 2 from the lone pair. It's got 1 from each of the bonds. Carbon has 5. It wants to have 4. So carbon has a -1 formal charge. It's got 1 extra electron versus what it would normally have, or what it would prefer to have, which is 4. For our nitrogen in the middle, it would like to have 5. Okay. Just squinting at my iPad to see if I saw any more Lewis or resonance structures. So our nitrogen in the middle, 1, 2, 3, 4 in these green dots. It would like to have 5. It has 4. So that puts it at a +1 for its formal charges. And then last but not least, our nitrogen on the right gets 1 from each of these bonds, +2 from the lone pair. So it has a formal charge of 0. Questions about getting those formal charges? Okay, and then for the one on the left, we also have to do formal charge counts. And we'll use the math approach to do this, the formula version. So formal charge for carbon, for nitrogen on the left, for nitrogen on the right. Carbon would like to have 4 because that's its number of valence electrons. We can subtract from that the number that it owns, which is 0 from lone pairs, or non-bonding, and then 1/2 of 8 from the bonds. So that's going to be a 0. The nitrogen on the left would like to have 5, because it's a nitrogen. It's got no lone pairs, and it also has half of the electrons from its 4 bonds. So that puts it at 5 minus 4, which gives it a +1. We'll go ahead and write those numbers in. And then the nitrogen on the right would also like to have 5. It has 4 electrons from lone pairs. So we get a 4 for the lone pairs part, and add to that half of the 4 that's in this double bond, 1/2 of 4, which is going to give it a total of 6, which means that it has a -1. It's got 1 extra electron. Questions about procuring those formal charges? Okay. Discuss with a neighbor which of these two structures, the left one or the right one, you think is better based on the formal charges. Yeah, it would be this left one is the better resonance structure. Why? In the left structure, nitrogen has the -1. In the right structure, carbon has the -1. Nitrogen is closer to fluorine than carbon is. It's going to have a higher electronegativity value. It's like 3 versus 2.5, if I'm remembering correctly. And so putting the negative charge on the nitrogen is better. So that's why the left one here is better. Questions? Okay, we can also have, because there's not enough exceptions to the octet rule, we can have odd electron species. And a class of odd electron species are free radicals. So free radicals are molecules and ions with an odd number of electrons in their Lewis structure. These will have a single electron somewhere in their Lewis structure. They're going to have just one dot instead of a lone pair. These tend to be unstable and reactive. Like, they won't exist for very long. Usually if free radicals exist, they are generated and then they disappear again. Yeah?
Do they exclusively contain oxygen?
It's not, I don't think they exclusively contain oxygen, but oxygen does tend to form free radical species. Yep. That's all I have to say about that. So for example, NO, nitrogen 5 electrons, oxygen 6 electrons. They're bonded to each other. We would have 9 more electrons to place. 5, 6, 7, 8, 9. Like that. I think that's correct. Yeah, that works. And the other way that you could think of to draw it would be something like that. Formal charges, you would find out that the one on the left is correct. So if we look at the formal charges of this one here on the left, the nitrogen has 2, 4 from lone pairs. It's got 1 more from the bond, so it has 5. That's the number that it likes to have. Oxygen on the right has 2, 4, 5 from lone pairs plus radical, and then 1 more from the bond, so that gives it 6, which is what it wants to have. So that's 0 for formal charges. And the version over here on the right, our oxygen would end up having a +1 and our nitrogen would end up having a -1 for their formal charges. So our Lewis structures sometimes will have free radicals. We will just try to get as close to an octet as we can. If we look at our oxygen in the correct structure, we've got 5 electrons for octet from lone pairs plus radical. We've got another 2 from the single bond. So it's only got a count of 7. And our nitrogen would have a count of 6. So we'd probably have to have a double bond in there. So that's fun. It would be this. That's probably more correct. I don't know, they're weird. Odd electron species. Which of these molecules would you expect to be a free radical? You don't have to draw out Lewis structures for this, you just have to do a little bit of counting. All right, figuring out which one is most likely to be a free radical, we just need to count up the number of valence electrons. Carbon has 4, oxygen has 6, so we're going to have 10 valence electrons for carbon monoxide. CO2, we've got 16 valence electrons. In C, we've got 2 times 5 for the 2 nitrogens plus another 6 for the oxygen. We also have 16 valence electrons. And in D, chlorine has 7, oxygen has 6, so we're going to have 13 valence electrons. This one is the only one with an odd number of electrons, and so this is going to be our free radical species. So that's the fast way to find the free radical. All right, I alluded to expanded octets, and I forgot that incomplete octets was the next slide. There it is, look, expanded octets, it's on the next slide. So incomplete octets are possible. Boron, for example, likes to form compounds that only have 6 electrons, which makes boron kind of weird, quirky. So boron, if it makes a compound, boron is going to be our central molecule. Fluorine only likes to have 1 bond. We'd count up our electrons, we'd add in our bonds, we would place the rest of our 18 remaining electrons, and we would get something that looks like this. That's all of our electrons placed. And boron is actually happy with this. If we look at formal charges, we can maybe see why. So let's look at formal charges. All the fluorines have the same setup. Fluorines want to have 7, because 7 is the number of valence electrons that they're bringing to the table. They would like to walk away with the same amount. If we look at our fluorines, they've got 2, 4, 6 from the lone pairs plus 1/2 of the bond, which is another 1. So that's going to give them a 0 formal charge. So that's for all of our fluorines. They get 0s for their formal charges. If we look at our boron, how many valence electrons did boron bring to the table? 3. So boron normally has 3 valence electrons, and if we count the number of valence electrons that it has, it's getting 1 from each of these bonds. Half of each of the bond is going to boron for our formal charge count. So it also has a 0 formal charge. If we were to make a double bond, one of the fluorines, wherever we make the double bond, would have a +1 formal charge, and the boron would have a -1 formal charge. Zeros is better than plus and minus. So this, based on formal charges, is the best way to make that Lewis structure. So boron's a little weird in that way. Beryllium will also tend to have incomplete octets. I don't know if we'll see that ever in the class. We can also have, as I alluded to earlier, expanded octets. So some Lewis structures, in order to get good Lewis structures, we have to go above our octet count, our 8 count. So we can go up to even 12 or 14 electrons. Let's look at Lewis structures for these two compounds. If we look at AsF5, arsenic is going to have 5 valence electrons because it's in group 5A or 15. And then we've got 5 times 7 for our fluorines. So that's going to have a total of 40 valence electrons. Fluorine only likes to bond one time, so arsenic is going to be our central atom. We connect our 5 fluorines, and we've used 10 electrons with making those 5 bonds. So we've got 30 remaining electrons. Each of our fluorines has 2 electrons. It would like to have 8. The difference between 2 and 8 is 6. So each of these fluorines can take another 6 electrons, and we've got 5 of them. 6 times 5, we can place our 30 remaining electrons on those fluorines. So we put in a bunch of double dots. Doesn't really matter where, and you end up with something like this. When we do that, fluorine has full octet. Arsenic has 10 electrons, 2 from each of the 5 bonds. We could do the same thing with SF6. With SF6, it would be sulfur in the middle, and we would have fluorines around it. I'm going to skip all of the counting. All the fluorines get 6 electrons in lone pairs. And that should be our final Lewis structure. These are both stable compounds. These will just hang out, they'll exist. They don't like decompose or just randomly disappear. And the reason for that is because arsenic and sulfur both have access to d orbitals. So sulfur is in row 3. So its highest n number is n equals 3. It also has access to d orbitals. We wouldn't fill up the d orbitals usually. We wouldn't fill them up yet. But because it has access to them because of being in row 3 or lower, we can store some extra electrons in those d orbital pockets. Arsenic being in row 4 also has access to d orbitals, and it can put electrons into those d orbitals. Questions about expanded octets? Yeah.
So arsenic only has 5 valence electrons in this case, right?
It So arsenic has 5 electrons that count for it for formal charges. It also wants to have 5, because that's how many valence electrons it brought to the table. So it's got a formal charge of 0, but it has 10 electrons on it.
Oh, yeah.
5 times 2 bonds.
Yeah.
Yeah. So expanded octets are available for elements in row 3 or lower. You will never find expanded octets for anything in row 1 or row 2, because they don't have access to d orbitals. You would have to bypass the 3s, 3p to get to the 3d orbitals, and that's just not favorable. Okay, let's look at formal charges on H2SO4 with and without expanded octets. Sulfur is going to be the star of our show here. And we are going to attach everything pause. Psych, we are not doing that. It is sulfur in the middle attached to oxygens, and 2 of these oxygens get also a hydrogen on them. Okay. We've got 32 electrons, 32 valence electrons. We have put in 1, 2, 3, 4, 5, 6 bonds. So minus 12 bonding electrons. We've got 20 remaining electrons that we can give to our oxygens. These oxygens that already have 2 bonds only want 2 more pairs of lone pairs. 2, 4, 6, 8. So we're going to subtract off 8 for those. That leaves us with 12 electrons. And each of our terminal oxygens can take 6. So this structure, we've placed all of our electrons. We check our octets. Hydrogen has 1 bond. They've got their duets. Great. Our terminal oxygens have their duets. And our oxygens that are not terminal also have their octets. This is an acceptable Lewis structure. It's not the best Lewis structure. And the reason it's not the best Lewis structure is because of formal charges. So let's look at formal charges in blue. Our hydrogens are going to have zeros because they have their 1 bond, so they're always going to be 0. If we look at everything else, we've got the left and right oxygen. So this oxygen would like to have 6. It has 4 from lone pairs and another 2 from the 2 bonds. So it has a 0 formal charge, and that's going to be the same for the one on the right. That leaves us with the top and bottom oxygens. So this top oxygen also wants to have 6. It has 6 just from the lone pairs, and then it gets 1 more from the single bond. So a total of 7. That's going to give it a -1 formal charge. Our bottom oxygen is the same. It's also going to have a -1 formal charge. H2SO4 overall is neutral. Our sulfur would have to pick up the slack with a +2. We can also do the maths on that. So it wants to have 6 electrons. It's got 4 bonds. It's taking half of each of those 4 bonds. So that gives it a 2+ for its formal charge. Questions on how we got any of those formal charges? This is if we have no expansion for our octet. So not expanded. If we expand the octet on our sulfur is the only one that can access expanded octets because oxygen is in row 2, sulfur is in row 3. Sulfur is bigger, it has access to d orbitals, it can have an expanded octet. If we computer expand, then this is going to give us the option to lower our formal charges. How can we lower our formal charges for our oxygens on the top and the bottom? Any ideas? Double bonds. So if we expand our octet on our sulfur, we can plop some of these electrons in as double bonds with our sulfur. And then we'll reevaluate. Our formal charges. So now if we look at the top and bottom oxygens, we want 6. We've got 4 from lone pairs minus 1/2 of the 4 in the double bond. Or if you count the number of points that are contacting the oxygen, it's 6. Same way, or same count. That's going to give it a formal charge of 0. Our oxygen on the bottom is going to have the same situation. And now if we do a count for our sulfur, it wants to have 6. It's got 0 electrons from lone pairs, and it gets half of the 2, 4, 6, 8, 10, 12 electrons that are in bonds. Or we can just count up the number of lines that are touching. We'll get 6 that way as well. So it also has a formal charge of 0. So by expanding our octet and adding in these double bonds, according to formal charges, we've made a better Lewis structure than the not expanded octet version. So this structure on the right is good because it lowers our formal charges. Questions about how much fun we're having with formal charges? Okay. Some for you to try. Write the Lewis structure for xenon tetrafluoride and for phosphoric acid. If necessary, expand your octet. For H3PO4, the phosphorus is going to be bonded to the 4 oxygens, and then hydrogens will be bonded to 3 of those oxygens. Okay, xenon tetrafluoride. We've got xenon, we've got fluorine. We've got 4 fluorines, each bringing 8 electrons to the table. Xenon is bringing 8 electrons to the table. So we've got 28 plus 8 for a total of 36 valence electrons. Our format, our skeletal structure, is going to be xenon in the middle and the fluorines on the sides. To get everything connected, we add in some bonds. So minus 8 bonding electrons, that gets us down to 28 remaining electrons. How many electrons can we give to each fluorine? How many more electrons can we put on each fluorine? It's a number between 0 and 8. So you get a 12.5% chance, assuming you don't get 0. You get a 12.5, it's 6. So we add 6 to each of them. So that's 6, another 6, that's 12, another 6, that's 18, another 6, that's 24. So minus 24 electrons to fluorines. And I'm going to scoot this whole thing over. Shoop. Oh no. Okay. We have 4 electrons left. Our fluorines have full octets. Right, they've got the 8 electrons that they want. We cannot give them any more electrons, but we still have 4 more electrons to place. Where can we put more electrons? If we can't put it on the fluorines, what's our only option? The xenon has to take the 4 remaining electrons, and we have to give them in as lone pairs. We have to give them in as lone pairs because if we put them in as bonds, then that would also be contributing to fluorine, whichever ones we affected. It would also be contributing to their octets, and we can't do that because they're in row 2. They don't have access to expanded octets. Xenon, being way down here, has access to expanded octets. If we were to check formal charges, we've got 0 formal charges for all atoms. Okay, and then a Lewis structure for phosphoric acid. We've got phosphorus in the middle, oxygens all around, hydrogens attached to 3 of them. We've got 32 valence electrons. We have to place a bunch of bonds, 14 electrons from bonds, which leaves us with 18 remaining electrons. We can place those remaining electrons for, why did I put them there? Going to each of these. So our non-terminal oxygens. And then we can also put 6 on our terminal oxygen. And that's all of our electrons placed. If we do octet counts, happy octets all the way around. We love that. if we look at formal charges, hydrogen wants to have just one bond. It's going to have zeros for their formal charges. Oxygens, the non-terminal oxygens, have 2, 4 from lone pairs, plus another 2 from the 2 bonds. So 6 minus 4 plus 1/2 of 4 equals 0. Or if you just put a dot on the end of the bonds, it's got 6 just right around it. So those also have formal charges of 0. The last two things to check is our terminal oxygen. Our terminal oxygen, 6 minus 7. Gives us a formal charge of -1. And then our phosphorus in the middle would like to have 5. Sadly, though, it only has 4. So that's going to give it a +1 formal charge. -1, +1, not the craziest thing in the world, but we can do better. And we can do better with expanded octets. And now I get to trim all of this. Okay. Get rid of that. Boop, boop, boop. There we go. So our OHs all have, they're all fine, right? So let's ignore those and focus in on our phosphorus in the middle and our terminal oxygen. The way that we can adjust the formal charges is we need to get some electrons off of our oxygen, off of our terminal oxygen. So we can make a double bond. And when we make that double bond, our count for this top oxygen, it wants to have 6. It has 6. It's got 4 from the lone pairs, plus another 2 from the double bond for 6. Our phosphorus in the middle wants to have 5, and now it has 5. It's got 1 from each of the 5 bonds, so it also has a formal charge of 0. Phosphorus can have an expanded octet because it's in row 3 or lower. So that helps minimize our formal charges. Zeros around. Questions? Great, we'll stop there and talk about bonds, bond energies and bond lengths, I guess, next week.